Hi everyone. Today we're going to derive all of the derivatives for the inverse trigonometric functions, and rather than just simply appealing to the formula that we derived in the previous video or just stating them for you, I think it's really instructive to go through to use the same ideas that we used in the proof for derivatives of inverse functions. So we're going to do this every time that we will find a new formula for derivatives of the inverse trigonometric functions. So let's get going. I know what you've been thinking. You say, boy gee howdy, I love taking the derivative of sine of x, right? Absolutely, me too. But suppose we wanted to find, not suppose, I mean we do want to find it, right? It's our burning question. How do we find dy dx if y is equal to the inverse sine of x? How do we find dy dx if y is equal to the inverse sine of x? And again, rather than simply appealing to a formula or telling you what the formula is, let's use the same trick that we used in the last video. If y is equal to the inverse sine of x, that means that the sine of y is equal to x by the inverse function property. And now let's differentiate both sides with respect to x. The derivative of the left-hand side, well, the derivative of sine of stuff is cosine of stuff times the derivative of what's inside, which is dy dx. And the derivative of the right-hand side with respect to x is just 1. And so now we can solve for dy dx, can't we? Dy dx is equal to 1 divided by the cosine of y. But what is y equal to? Let me just write y. But what is y equal to? It's the inverse sine of x. And we could leave it like this, but literally nobody does that. So instead, let's use our trigonometry knowledge to get this as an expression that might look better. To do that, we're going to draw a nice triangle. Yeah? And recall from trigonometry that if arcsine of x, I know that that outputs some angle theta, yeah? Then that means that the sine of theta is equal to x divided by 1. And we can use this information to label our triangles. If sine of theta is x divided by 1, then I know that the opposite has to be x and the hypotenuse has to be 1. And by the Pythagorean theorem, I have that the adjacent side length has to be 1 minus, or square root of 1 minus x squared. Well, what do I really want to compute? I don't need theta, I need the cosine of that angle theta, right? Arcsine of x is this angle theta. So what's the cosine of this angle theta? We have that dy dx is 1 divided by, what's cosine of this angle theta? It's adjacent divided by the hypotenuse. So it's just the square root of 1 minus x squared. And what's the domain of this function? Certainly x can be any number between -1 and 1, but it cannot equal that, -1 or 1. So we have to have that x is in the interval strictly between -1 and 1. Yeah? And that's kind of interesting. What's really cool, so let's sit on this for a few seconds. What's really interesting here, we started off with a purely trigonometric function, but the derivative has no trigonometric functions in it. And that's really interesting. It's only a rational function with a square root in there, and it's really, really interesting and unexpected, I think. Let's do another one. Let's find dy dx if y is equal to the inverse cosine of x. All right, so you know exactly what we're about to do, so go ahead and pause the video, try to work this yourself, and then check your work with me once you have an attempt, okay? All right, so let's jump right in. We're going to unpack this using inverse functions. So really, we want to differentiate both sides of the equation. Cosine of y is equal to x. Well, whenever we differentiate both sides, we see that we have negative sine of y times dy dx is equal to 1. And now we can solve for dy dx, just like we did in the previous example. Dy dx is equal to 1 divided by, or negative 1 divided by the sine of y. And what's y equal to? Arc cosine of x. So it's negative 1 divided by the sine of arc cosine of x. And it looks very, very similar to the expression that we had in the previous example, right? So let's unpack the denominator just like we did before. And we're going to use triangles to help us out. What's that angle theta in my right triangle that I drew? That angle theta is the inverse cosine of x. Remember, because the inverse trigonometric functions spit out angles. They take in values, they spit out angles. And if arc cosine of x is equal to theta, then the cosine of theta has to be equal to x over 1, right? And so now let's label our triangle. Cosine of theta is x over 1, so that's adjacent, divided by the hypotenuse. So that means that this other adjacent side has to be square root of 1 minus x squared again. So what does that mean for our derivative dy dx? It's negative 1 divided by, what's the sine of this angle theta? Right? Because we only need the sine of that angle theta. It's once again the square root of 1 minus x squared on the same domain, where x is in the interval negative 1 to 1. Yeah? It's kind of cool. So it's exactly the same as the derivative of inverse sine, except there's a negative. And that's kind of interesting. Let's do another one. Try to find dy dx if y is equal to the inverse tangent of x. Okay? Pause the video, try this yourself. Alright, so we'll play the same game. We'll unpack it using inverse function properties. So we have that the tangent of y has to be equal to x. We differentiate both sides. The derivative of tangent of stuff is secant squared of stuff times the derivative of what's inside, which is dy dx. And the derivative of x with respect to x is 1. So solving for dy dx, it will look a little different now. Dy dx is equal to 1 divided by the secant squared of y. But we know that that's equal to cosine squared of y, so that's kind of interesting. All right, and what's y? Cosine squared of y is the arctangent of x. So let's use a triangle to rewrite this. Remember, we're going to be able to get all of our expressions without trigonometric functions, so that's kind of a cool feature of this. Let this be my angle theta, where that angle theta is the arctangent of x. So if arctangent of x is theta, that means that tangent of theta is equal to x divided by 1. Well, if tangent of theta is x over 1, that's the opposite over adjacent. By Pythagorean theorem, my hypotenuse is 1 plus x squared. Yeah? And so, what's dy dx? It's going to be the cosine. Well, what's cosine of theta? It's the adjacent divided by the hypotenuse. So it's 1 divided by the square root of 1 plus x squared quantity squared, right? Well, if I square the numerator, I just get 1. And if I square the denominator, notice that this is always a positive function down here. There's no domain restriction there, right? So there's no absolute value or anything. It's just 1 plus x squared. Everything's positive, okay? And that's kind of nice. Let's do one more. Let's try to find a formula for secant, inverse secant. Find dy dx if y is equal to the inverse secant of x. Pause the video, try this yourself. There's a little wrinkle at the end, but we'll talk about that together. Alright, so let's unpack this. We have that this is exactly the same as saying that the secant of y is equal to x. Yeah? Let's differentiate both sides with respect to x. dy dx. Oops. Well, I need to put my secant y, tangent y. Sorry about that. What's the derivative of secant stuff here? It's secant stuff, tangent stuff, times the derivative of what's inside. And the derivative of x with respect to x is 1. Sorry about my messy work here. Let's solve for dy dx. dy dx is equal to 1 divided by secant of y times the tangent of y. And what's y equal to? Well, it's the secant of arc secant of x times the tangent of the arc secant of x. Yeah? Well, this one looks super nice, doesn't it? Yeah? That one looks super nice. But what about how do we unpack the tangent of arc secant of x? Well, let's draw a triangle again. This angle theta is the arc secant of x. So that means that the secant of theta is equal to x. Okay? And of course we divide by 1. So it's going to be the hypotenuse divided by the adjacent, x divided by 1. And what goes on the opposite side? It's the square root of x squared minus 1. And now what is tangent of theta? We get that dy dx is equal to 1 divided by secant of arc secant of x is x, square root of x squared minus 1. Because remember, what's tangent of theta? Tangent of theta is opposite over adjacent, which is the square root of x squared minus 1. What's interesting here is that we have made an assumption. We have made an assumption that x is positive. Yeah? Because remember, x is here on the hypotenuse. If it was negative, something weird would have to happen. We would really need to put a negative 1 on this adjacent side. If x was negative, we would really need to fix it by putting a negative on this adjacent side. If we have a negative on this adjacent side, then the tangent of theta would end up being negative. So dy dx is equal to this quantity whenever x is strictly bigger than 1. Right? That's your domain restriction in the bottom. And by a similar argument, dy dx will have to be 1 divided by negative x square root x squared minus 1, where x is less than negative 1. Yeah, if x was negative, you would have a negative that pops out whenever you compute this tangent. So whenever you put this together, what function do we have that is x whenever x is positive, but negative x whenever it's negative? That's an absolute value, right? So the formula that we'll use, always and forever, is that dy dx for arc secant is 1 divided by the absolute value of x times the square root of x squared minus 1. Okay. Let's do some examples together and compute some of this. Compute the derivative with respect to x of the tangent of 3x plus 10. Okay. Pause the video, try to compute, oh, the inverse tangent, sorry. Pause the video and try to compute this yourself. Alright, so we know that the derivative with respect to x of arctangent of stuff is 1 divided by what? 1 plus stuff squared. Yeah? And my stuff here is 3x plus 10. And now chain rule happens. So now we need to multiply by the derivative of what's inside. The derivative of 3x plus 10 is 3. And that's our derivative. Okay? Let's do another one. Compute. The derivative with respect to x of the arcsine of 5x squared. Pause the video, give it a shot. So we know that the derivative of arcsine of stuff is going to be 1 divided by the square root of 1 minus stuff squared, right? And what's my stuff? It's 5x squared. Now we need to do chain rule, so now we multiply by the derivative of what's inside, which is times 10x. Yeah? Cool. Well, I think this is all that we need to talk about today, guys. I'll post some more homework for you. If you have any questions whatsoever, feel free to reach out via email, or we can set up a time to meet in Zoom. And I'm happy to help in any way that I can. Thanks so much for watching, everyone. I look forward to seeing you in the next video.